All right, ladies and gentlemen, this is our last section before our Chapter 4 test, and we're talking about similarity and transformation. So a dilation is a transformation that preserves shape but not size. So a dilation is a non-rigid motion. All the other ones we talked about, rotations, reflections, and translations, were all rigid motions. So a similarity transformation is a dilation or a composition of rigid motions and dilations. So two geometric figures are similar figures if and only if there is a similarity transformation that maps one of the figures onto the other. Congruence transformations preserve length and angle measure. When the scale factors of the dilation is not equal to 1 or negative 1, similarity transformations preserve angle measures only. So that's basically just a synopsis of that first paragraph. All right. So it's basically saying the same thing. Remember, if it's 2 or negative 2, right? It's going to be a dilation. If it's 1/2 or negative 1/2, it's going to be a dilation. The negative would actually make it a reflection. And we'll see that here in this first example. So graph line segment AB with endpoints A at 12 and negative 6, and B at 0 and 3. And its image after the similarity transformation of a reflection in the y-axis and a dilation of xy maps to 1/3 x, 1/3 y. So I had made your points there, but I did actually labeled them wrong. So A is at 12 and negative 6, and B is at 0 and negative 3. So remember, a reflection in the y-axis will change the x-coordinate. So xy will map to negative x and y. So if we think of it that way, let's see. A, which is 12 and negative 6, will map to A prime, which will be negative 12, negative 6. All right, so that'll be negative 12, negative 6. That'll be A prime. And then our B, which is 0 and negative 3, well, since that is on the line of reflection, it's not going to change. Remember, if it's on the line of reflection, it'll stay the same. So our B prime will be there. And you'll see why I put it down there in a second. And again, draw the line. Doesn't have to be perfect. Well, we both know that. So then, again, remember, I also told you, ladies and gentlemen, you could just count. Since they said in the y-axis, you could have gone and just counted 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Since we said it was over the y-axis. All right, that's the second way I showed you. All right, now with the dilation, again, they're saying we're going to take our xy, which this time, again, since it's a transformation, we have to use the A prime. All right, so our A prime, we went from negative 12 to negative 6. So that'll map onto our A double prime. So 1/3 of negative 12, or negative 12 divided by 3, will give us negative 4, and negative 6 divided by 3 will give us negative 2. for B prime, which was at 0 and -3, we're going to map that to, well, a third of 0 is 0, and a third of -3 is -1. So again, we're going to have B double prime at 0 and -1. Our A prime we said was at -4, -2. And then we are going to draw. And that is our dilation, the last one. And again, we should know that because of how they're labeled. All right. And then our last example here, describe a similarity transformation that maps trapezoid WXYZ to trapezoid PQRS. So on this one here, I'm going to show you two methods. Well, method one is the one that the book likes to show you, so I'm going to show you that. Okay, and they're going to tell you to first find the coordinates. So we'll get that W is at 2 and 1. That X is at 1 and 1. Y is at 0 and -1. And Z is at 2 and -1. Our P will be at 4 and -2. Our Q is at 2 and -2. Our R is at 0 and 2. And our Z, S, is at 4 and 2. All right. So now they're saying, kind of look at where they did now. They're kind of trying to do the same thing I do. But first, the thing is you'll notice that you're going from 2 to 1, and the point that corresponds to it is P, which is 4 and -2. So if you look at it, first thing you should notice is you have a dilation. Because if we look, our X and Y will go to 2X, 2Y. So if that's the case, our W, which is at 2 and 1, goes to W prime, which is at 4 and 2. Similarly, our X maps to 2 and 2. Our Y maps to 0 and -2. And our Z maps to 4 and -2. All right. So then we know if we look at these, like W prime, I have 4 and 2, but I need 4 and -2. So what you should recognize there is that we're going to be reflecting it, okay? It reflects in the x-axis. So a reflection in the x-axis which will tell us that xy and a reflection in the x-axis means our x stays the same, our y is going to change. All right, so then again, let's see if this is true. So then we have our p. Our p is, our w prime is at 4 and 2. So our p would be the x stays the same and the y changes, which is true on that one. And what you should see is that all of these, it's going to be the same. The x value stayed the same, and the y value is the one that switched. So on here, our answer would have been a dilation of 2 and a reflection in the x-axis. All right. So method 2 is similar. All right. I'm just kind of going to tell you this here. So focus on a pair of corresponding sides. And I know I'm going to go down here. So choose the one that you like as you're writing your notes. So method 2, I want you to focus on a pair of corresponding sides. All right. So the 2 I'm going to focus on is this one here. I'm going to focus on WZ, and I'm going to focus on SP. All right. So what you have to do is say and think about these questions. All right. What dilation makes them the same size? Well, if it's still 1 or -1, you know they would be the same size. But on this one here, again, we're going from the small one to the large one, right? So in this case here, I can see that my distance here is 2. My distance here is 4. So there was a dilation on this one here. So our dilation, again, was our dilation was 2. So again, we went from xy goes to, or maps to, 2x, 2y. So we did use that one. I'm going to write them all down here, even though we're only going to use 2 of them. So the second question you can ask yourself, does the orientation need to change? Okay, if the orientation changes, that means there's a reflection. All right, so again, if you think about it, the WZ, it flipped based on the first one that we did there, it did flip, right? It flipped over the x-axis. So in this case, we know that that one was true also. So we had what? On that, our xy, again, When it changes on there, our x stays the same, our y becomes a negative of whatever we had. So on that one, it was also true, right? So on that one there, we could have said, again, based on that I had this one here, and I had this one here, again, you could tell me it was a dilation of a factor of 2 and a reflection in the x-axis. But again, I want you to think of the other two. There's two more, because remember, we have rotation and we have reflection. So our other ones we can ask is, does the location need to change? So if it's location, that would mean it would be a translation. Okay, and that would be moving the x and the y, like x maps to x plus 6, y maps to y minus 4, that kind of thing. All right, and then the last one is, does the position need to change? And if that's the case, then again, you'll have a rotation. Remember, you can have a rotation of any degrees from 0 to 360. All right? So let's look at the keywords here that will help you out. Well, dilation, same size, right? So let me go ahead and do that. So dilation, same size. Orientation is a reflection, right? A location is a translation, and then a position is a rotation. So I started the two that we used here, and what happened to it, again, the location I kind of told you. Again, I told you what the position is. Hopefully that'll help you, ladies and gentlemen, as you do your homework. All right? Thank you.